Welcome back. So we've seen the cosmic microwave background radiation. We saw its spectrum from the COBE satellite. This is so interesting and important and useful that another dedicated satellite was launched in the late 90s called the Wilkinson Microwave Anisotropy Probe, or WMAP. You might remember Wilkinson is the guy who didn't win the Nobel Prize from physics from Princeton because even though he predicted it, because Penzias and Wilson found it first. Well, he got his name on a satellite, so that's not so bad after his death, but still. And so they mapped out, this is what the cosmic microwave background looks like. And what you're seeing here in blue and red is a temperature map. So what are you looking at here? You are looking at very small fluctuations, perturbations in the temperature. This is a very high contrast map, right? So this is all 2.7 Kelvin. In fact, let me try to bring this up. I should have done it before I started this video, but of course you can't open the specified file. Let me try to bring this up because I think this is an important thing to see. 030, let's see. This is, okay, tell me. Five, three. Okay, I want to show you what this looks like because this is telling you how important this WMAP probe was. Let me share QuickTime Player. Okay, here's the little movie. It's only a 6-second movie, but this is the COBE. This is the resolution of the COBE satellite, right? It could map out these temperature fluctuations, but WMAP increased the resolution, spatial resolution, by an order of magnitude or more. And so now we can really, these are actual blobs. And this is important because, let's go back to our PowerPoint. Here we go. This is important because now, again, these are all in thermal equilibrium, but now you're seeing small fluctuations in the actual early universe matter distribution. And that's extremely useful and helpful. And so these are real blobs. These are real sized chunks of the early universe. And we can use the size of these blobs and also their temperature variation to give us insight about what the conditions were like in the early part of the universe to amazingly high accuracy. So for instance, the size, you can see the size of a typical blob here is about this, right? There's a typical blob. You see a lot of these typical blobs there. The size of a typical blob actually tells you the geometry of the universe. It tells you whether the universe is open or closed. And I want to talk briefly about why that is. Let's, oops, I know that. I should have queued all these up. Full sky and all wavelengths. Let's, I'm gonna play this one too, because it's important. Here is a, let me share this particular movie with you. This is a longer video that shows, so it's going to zoom into us and our location in the Milky Way. It's going to show you what the all sky background looks like in the visible part of the spectrum. It's going to take the entire sky. Again, we're seeing the entire sky spread over a single sheet. Unfold it, lay it down so that the galaxy is at the center. We've seen these kinds of diagrams before. And now we're going to go to the microwave. And we're going to take out all of the known sources that we know of in the, so this is important, right? This is what the cosmic microwave background really looks like. It's all 2.7. We have to increase the contrast by orders of magnitude to really see what's going on. And so there's very small differences in temperature between a red blob and a blue blob. This shows the galactic sources that have been taken out in our other diagram. But this is showing you very, very small temperature differences, like 0.0001, something like that, between the red blobs and the blue blobs. So it's a very high contrast map. Anyway, that's important to understand as you're seeing these diagrams. Going back to PowerPoint, there we go. We need to understand how the size of these blobs are affected by the geometry of the universe, right? So this is a diagram that tries to explain it. Oh, look at that. That's not very useful. When I print these out, I will try to make sure that this text is actually visible there. But the size of these fluctuations, what it says, the size of these fluctuations determines the geometry of the universe. Let me show you this one. This is 39b. This is the Kobe satellite. This is the WMAP satellite. And you can see how the geometry of the universe is going to affect these things. There's a flat universe, you get a certain size of blobs. If you make the universe open, let's see if we're going to see the open universe next. A closed universe, the blobs look bigger. An open universe, the blobs look smaller. Let's try to figure out why that is. You can sort of see it here, but I want to show you why that particular, I think it's better to show on the whiteboard. So let me show you the whiteboard. Okay, here's my whiteboard back. So what is the geometry of the universe? I mean, the geometry of the universe may seem like a trivial thing to you, but it's actually really profound, right? It has to do with the actual geometry of the universe. For instance, in a two-dimensional field, right, we know that triangles in normal flat space, you add up the angles and they all add up to 180 degrees. That is only true on a flat surface. If you were to try to do this on a spherical surface, right, I can show you a triangle on a spherical surface. In other words, you go in a straight line, you make a right turn, 90-degree angle, make another right turn, 90-degree angle, make another right turn, 90-degree angle, and have those three connected, right? These add up to way more than, let's add to 270 degrees, right? If you started the equator on the Earth, go straight north to the North Pole, take a right turn, go straight to the equator, take a right turn, go straight here. You have gone in 3 straight lines. They don't look straight on here, but they are on the surface of the Earth. And the corners add up to way more than 180 degrees. You can do the same thing. I can't draw this very well on a saddle-shaped sphere surface. And what happens is instead of so here's a triangle in a closed universe. In an open universe, it gets stretched in the other direction. And sides of a triangle add up to less than 180 degrees, right? That's sort of what the geometry does for you. So as we're sitting here in the bottom, let's say this is the Earth, and we've got some blobs of the universe. Let's just put them here. We know what the characteristic actual size of these blobs was, right? As we look out, we get a certain field of view, right? In a flat universe, that field of view contains a certain number of blobs. These, in a flat universe, seem to be straight to our top-down view, and you get a certain number of blobs. You get a certain size of those blobs, right? This has some angle. You can figure out what the angular size of each of these blobs is. Well, in a flat universe, in a closed universe, what happens? Well, we know that the geometry of that isn't that these, what happens to 2 diverging lines, right? Let's think about this on a sphere, right? If you're standing on the top of a sphere, and 2 people start walking in slightly different directions outwards, those 2 people will eventually meet at the bottom, even if they go straight, right? So diverging paths actually tend to converge back onto each other. That's going to look like this, right? So in a closed universe, we expect fewer blobs to be in the same field of view. The blobs, in other words, will appear bigger. And for a closed universe, for an open universe, it goes exactly the opposite. they diverge. And so we expect more blobs to appear in that same initial cone angle view. And so the blobs, there'll be more of them in that angle, and they'll appear smaller. So the size of these blobs is directly testing whether this field goes straight, expands, or contracts. And that tests the geometry of the universe directly. Okay, here we are. We're back. So so WMAP made a power spectrum of the microwave background. What is a power spectrum? This is a lot, but this is what a power spectrum looks like. What this is the higher this is on the y-axis, the more blobs have that characteristic size. And the smaller this is, the fewer blobs have that characteristic size. And so you can see that from WMAP, this is going in the opposite direction. This is very large blobs, this is very small blobs. The primary peak, most blobs appear at about 1 degree. WMAP was also sensitive to pick up a secondary peak and perhaps a third peak, and this is probably way too much noise to read anything into this, but clearly there are some peaks here. Now, this red curve represents a single universe that has a particular geometry, a particular Hubble constant, a particular value of how much matter there is in the universe. There are lots and lots of parameters that are contained in this particular red curve that fit this graph beautifully, right? And the size of the temperature fluctuations in the cosmic microwave background are what is giving you this curve. Now, this was so good and so cool and so useful that they announced another satellite in about 2010 called the Planck satellite that did even far better. This is a European satellite. This is the Planck map. Again, increased by orders of magnitude the accuracy, the resolution, the positional accuracy that it could get. And this is, again, a very high contrast view of what the actual cosmic microwave background looks like. And this same plot from Planck, you can see the initial peak at 1 degree, the secondary peak showing up beautifully, the third peak showing up beautifully. Look at how small these error bars are, right? They're big up here. They get tiny as you go smaller angular scale. Secondary peak, third peak, fourth peak, fifth peak, sixth peak, seventh peak. Very well measured and resolved. And again, this green line is a single universe that has a particular geometry, a particular value of the Hubble constant, a particular amount of dark matter, a particular amount of normal matter, a particular amount of dark energy. And if you change any one of those parameters even a little bit, the wiggles aren't quite the same and it won't match up as well. This is the most powerful thing we've done to discover what our universe is like. So what is the answer? What does the universe actually look like? Well, on the left, we've got what basically the WMAP gave us, that the universe was about 4.5% ordinary matter, about 22.7% dark matter, and about 73% dark energy. After Planck, well, it adjusted these numbers slightly, but not too much. A little more dark matter, a little less dark energy. Ordinary matter, almost 5% of the total energy of the universe. Dark matter, almost 27% of the total energy of the universe. Dark energy, 68, the rest of it, 68.3% of the universe. And these are our best numbers to date. Nobody has done better than this. So our results from Planck were this. The overall geometry is flat. The total mass plus energy, that omega total, is 1 within a 1%, 1.01 or something like that. Total matter is about 32% of the total, with 5% of that coming from ordinary matter and 27% coming from dark matter. Dark energy is the rest of the 68%. The age of the universe, this is amazing. When I took astronomy, and this was a while ago now, what, 20, 25 years, the age of the universe was somewhere between 10 and 20 billion. We didn't know. The Hubble constant was somewhere between 50 and 100 kilometers per second per megaparsec. We didn't know. we have four significant figures on this now. 13.82 billion years. Not 13.9 or 13.7, 13.82 billion years. The Hubble constant, 67.8 kilometers per second per megaparsec. This is again, in the past 25 years, we have gained orders of magnitude, several orders of magnitude in the uncertainties and the known values, the precisions of these values. It's a remarkable, remarkable achievement. The most amazing thing, though, that has come from these WMAP and Planck results are, this is the first time that we have ever increased our understanding of the universe's structure and content by an order of magnitude or more and not had it break all of our models. Right? Every other time we have gained a deeper understanding of the universe, it has broken the models that we had used to describe the universe, and we had to come up with new ones, which is exciting. That's not necessarily a bad thing. We like it when our models break because we learn new things about the universe. Here, we've increased our understanding of these cosmological parameters by a couple of orders of magnitude, at least. And the universe is what we thought it was. A place where there is ordinary matter and a lot of dark matter and a lot of dark energy. And so that is probably the most amazing thing of all of this. We have a consistent model of the universe that matches all of the known observations. Okay, ultimate fate of the universe. The universe is expanding, we know. The universe's expansion is accelerating. What is that ultimate fate? What is going to happen? This is kind of a fun story. Well, you know, fun if you're kind of a morbid person. So we are at year 10 to the 11 now, right? We're at 13, 14 billion years post Big Bang. That's a 1 with basically 11 zeros after it. We're going to throw out some very large numbers now and think about some very distant times in the past. So again, when I say year 10 to the 14, I'm talking about 1,000 times older than our universe is right now. I've just added 3 to this, but every time I add something to the exponent, I'm multiplying by that number of tens, right? So if the universe is 10 billion years old now, it will be 10 trillion years old at year 10 to the 14, right? That is 1,000 current ages of the universe from now. At that point, we expect all star and galaxy formation ceases. Basically, you've used up all the hydrogen gas in your galaxy and you can no longer form new stars. Another factor of 10 older than the universe, interesting things happen. It turns out our planetary system is not stable. Over very long time scales, it's probably unstable. The planets exhibit little perturbations on each other, and if those perturbations add up, eventually you can have planets colliding and getting tossed out of the solar system and tossed into the sun. And so on this time scale, planets' orbits decay. In other words, they fall into their stars or they're ejected from their stars. Well, that's no fun. On year 10, another factor of 10, stars, sort of the same thing, have close encounters with one another and are ejected from galaxies. And galaxies kind of cease to be a thing because all the stars get ejected. Now, we're taking a huge jump because there isn't, once you have all stars ejected from galaxies, you know, all of the low mass stars have burned themselves out. All of the high mass stars have burned themselves out. Remember, the sun will be dead in another 5 billion years or so. So all the suns are dead by this time. But the low mass stars also will start to decay. Will start to run out of hydrogen, right? They will start to go through their end of life sequences also. So you'll be left with, what will you be left with? A lot of stellar corpses, white dwarfs, neutron stars, black holes. That's what will be left from the year 10 to the 16 to the year 10 to the 36. Now, interestingly, we think that, we know the neutron has a half-life. A bare neutron will not last more than 13 minutes or 11 minutes or something like that. We think that the proton might also have a half-life. And if that's the case, we think it's something like 10 to the 35 to 10 to the 40 years, which is an extraordinarily long time, right? We're talking about 1 with 40 zeros after it. If it's 10 to the 36 years, half of them are, so let's say that proton half-life is achieved at 10 to the 36 years. At 10 to the 36 years, half of them are gone, right? At 2 times 10 to the 36, another half of them are gone. At 3 times 10 to the 36, 4 times, another half of them are gone, right? Every 10 to the 36 years, half of them are gone. Well, by the time you get to 10 to the 40, that's a huge number of halves, right? That is, I don't even know, thousands of halves. And so at that point, all of the protons are gone. In other words, even if you had white dwarfs and neutron stars, at year 10 to the 40, they're all gone. And they decay into photons and elementary particles and black holes. And so at year 10 to the 40, all you have left in the universe is black holes. Now, it turns out that black holes can decay too. We talked about this when we talked about black holes. Hawking radiation can slowly rob them of energy and mass. It takes a very long time, but hey, we're the universe and we can have 10 to the 100 years. 10 to the 100 is an extraordinary number. Let's just talk about 10 to the 100 for a second. Go to a whiteboard. Here's 10 to the 100, right? Let me write it down, 10 to the 100. Right, a 1 with 100 zeros. I'm not going to bother to write that. It would take me, I would have to go through, it would take me the whole whiteboard to fill 100 zeros here. It's a very large number. Some mathematician named this. In fact, he asked his daughter to help him name this number, and she came up with a Google. This number is a Google, G-O-O-G-O-L. And this is not the name of the search engine that you know as Google, but this is where Google got its name. The name for 10 to the 100. They just changed the spelling a little bit. But this is a Google, and it is a very large number, right? 1 with 100 zeros on it. It is, you imagine this, about the number of grains of sand that could fit in the visible universe. Think about that. Not on Earth, not in the solar system, not in our galaxy. The number of grains of sand that could fit in the visible universe is comparable to 10 to the 100. That's a big number. Okay, let's go back. We're almost done. Ten to the 100, most of the black holes have decayed, right? And by year 10 to the 115, all black holes have decayed and the universe is nothing but radiation. Not only that, the universe has stretched to almost infinity at this point. And so, you know, every visible universe contains roughly 1 photon or something like that. And at this point, not even any matter can interact with one another, or any photons can interact with one another. And we get to year to the 10 to the 500 or so, temperature reaches a constant, right? And that is basically the heat death of the universe. It's extremely cold. The temperature is basically 0. But we call it heat death because if you're a fan of the second law of thermodynamics, the entropy has gone to infinity. You have died of an entropy death. And that's what we think will happen. A very icy, cold end of the universe that we call heat death. Okay, basically all I have. I'm going to post one more video that will wrap up sort of the class and point you to another video. But that's basically all I've got. So hope you enjoyed.